Hello, and welcome to our session on expressions and equivalents. In this lesson, we're going to talk about what an expression is and exactly what it means for something to be equivalent to something else in a mathematical sense. Now, I'm sure you've actually heard of mathematical expressions before. Maybe you've heard a teacher talk about them or you've used them yourself. But the general idea is that a mathematical expression is really meant to be a series of steps that you're meant to follow to compute with numbers. Now, if you've ever looked at a piece of maths and felt like it was written in another language, you'd be about right, because a mathematical expression is literally another language. But it is a fair bit simpler than a language we'd usually use to communicate. Now, the main difference between a mathematical language and a language that we'd use to actually talk to each other is that a mathematical language is only really meant to represent a series of steps. However, representing a series of steps symbolically is actually incredibly useful. So just to show you this, I've started with a really simple mathematical expression here. The idea is that you start with the number 3, and then you add to it 4 times 2, and then you subtract off 7. Notice that we're actually giving you a series of steps that you need to follow. In a sense, when you're given this expression over here, you should think of actually performing the steps shown in the diagram over here. Now, I start with the number 3, so I'm going to write it on this line over here. We also have this 4 over here, which we can write here. But then what we do is we multiply the 4 by 2 to get this number over here, which will be 8. So I want you to imagine this 3 flowing down to this plus sign over here. Then I want you to imagine this 4 flowing to this times 2. And then you have this 8 flowing to the plus sign. Then you just have to perform the addition. 3 plus 8 is the same thing as 11. So on the other side of the plus sign, we have the number 11. After passing this plus over here, this 11 flows and hits the minus 7. 11 minus 7 is the exact same thing as 4, so we just get 4 on the output over here. So in a sense, this whole expression over here is equivalent to the number 4. Or if you like, we could say that it's equal to the number 4. Now this expression over here is a language. You can translate it into English. So I could say that this is 3 plus 4 times 2 minus 7. But it's more than just a normal language. It's really designed to give you a series of steps that you can actually follow to get an actual answer. Now, human languages can actually be ambiguous sometimes. If interpreted differently, the same sentence could mean more than one thing. This is also possible with the language of mathematics, which I can show you with a simple example. Now, I remember a while ago on the internet, this expression over here caused a huge firestorm. Nobody could really agree on what the actual answer was. And I think the biggest reason why people couldn't agree is because there are two different ways that people would interpret something like this. Now, when debating this expression here, people ended up in two groups. The first group had learnt BEDMAS when they were growing up, and the other group had learnt PEMDAS when they were growing up. There are variants of these, but these were the main two groups. BEDMAS tells you to do the brackets first, then exponents, then divide, then multiply, then add, then subtract. PEMDAS, on the other hand, says parentheses first, or brackets, then exponents, then multiply and divide before adding and subtracting. Now the simple idea is that this expression over here is ambiguous, and you should never write an expression that looks anything like this, ever. But if we were to follow BEDMAS, let's see what happens. It tells us to actually start with the brackets, so we have to look inside the brackets and add 9 plus 3 first. Next we look for exponents, but there aren't any exponents, so the next thing we should do is we should look for the division. Well, that means we're going to want to divide 48 by 2 in the next step, so let's write that down too. So first off, 9 plus 3 happens, which we've represented here. After this we have to take 48 and divide by 2, which we've done over here. Now between these two expressions there's an implied multiplication sign, so we have to multiply the result here by the result here. And then our answer would just be what we get after the multiplication. Okay, so let's work the answer out. 9 plus 3 is the same thing as 12, so we have 12 over here. And then you've got 48 divided by 2, which is the same thing as 24. And then 12 times 24 is the same thing as 228. You should probably check this with a calculator just to make sure. After this, we had the second group of people who looked at this a little bit differently. They were told to do the parentheses first again, so they just added 9 plus 3 to get 12 again. Now, this 9 plus 3 is represented by this term over here. There aren't any exponents, so they didn't need to do anything there, but there is actually a multiplication between this 2 and the 9 plus 3. This means that they needed to actually multiply this 9 plus 3 by 2, and if you did that, you got 24. So now we have this whole section over here, 2 times 9 plus 3, which is the same thing as 24, as we saw. After this, we just want to divide 48 by 2 times 9 plus 3, or 48 divided by 24. Now, of course, if you do things this way, you get the number 2. And that's impossible, right? You can't have the answer be 288 and 2. So you had this group of people on the internet arguing about whether the answer was 288 or 2. And this went on for way too long. Now, it turns out that neither of these groups were actually wrong, and I guess that's why they were arguing. It turns out that this expression over here is really the evil part. You should never write an expression like this. You always need to include brackets whenever there's a possibility for ambiguity to arise. Now, it turns out that most calculators are programmed so that the answer is 288. But you can avoid this problem altogether by just putting brackets where you need them. Now, if the person who wrote down this expression wanted it to represent this computation, they should have written it like this, putting brackets around here. If they wanted this computation, they should have put the brackets around here. And then in either case, both BEDMAS and PEMDAS would both agree on what the actual answer should be. This one will always be 288, and this one will always be 2. So I hope you can see why it's so important to make your expressions really clear. But there are actually a few other parts that we can put in expressions, so let's start talking about the anatomy of an expression. Now, expressions can be made up of a whole bunch of different parts, and the first of these is a pronumeral. A pronumeral is basically just a placeholder for a number. We can actually replace them for a number. For example, if we write 3 times x, we write it like this. The idea is you could replace this x for any number you like. And if we wrote something like y minus 7, we're just saying that you could replace this y for any number you like. And y minus 7 just tells you to subtract 7. After this, we can also talk about terms in an expression. Terms are basically just parts of the expression separated by a plus sign or a minus sign. For example, in this expression over here, we have 1, 2, 3, 4 terms. Now we can also look at the second example over here. On the outermost level, there are only 2 terms, as you can see. But this second term over here actually has what we'd call subterms, which are terms inside of terms. And it has 2 of those. Now, I think most of you will agree that 3 is the same thing as 2 plus 1. Or in more mathematical terms, we'd say 3 is equivalent to 2 plus 1. But we could also say something like 5 plus 2 is the exact same thing as 8 minus 1. Both of them lead you to 7, so both of these are actually equivalent to the number 7. But when pronumerals enter the picture, equivalence becomes a little bit more complicated. So let me write down what I mean by equivalence when pronumerals are involved. So if 2 expressions are equivalent, we're saying that no matter what values you choose for the pronumerals, the values produced by those 2 expressions always have to be exactly the same. Usually, we denote equivalence with an arrow or a triples equal signs. But another really popular way to denote equivalence, which is a little bit confusing sometimes, is to just use a normal equal sign. Now, the reason we can use equality in the place of one of these equivalent signs is because the difference between equivalence and equality isn't actually so huge. However, when you study algebra, you'll see that there are actually subtle differences, but they're so subtle that we don't really need to care about it all too much. But just to make things clear, I will tend to use this sign wherever I remember to, but again, you could also swap it with this sign over here. Now, in general, we can find some trivial equivalent statements by performing some simple arithmetic operations. For example, if you start with an expression and add 0 to it, Of course, these two expressions are going to be equivalent. Now, as you'll see throughout your studies of mathematics, adding 0 is one of the most powerful techniques that you can actually use. 3x, of course, is the same thing as 3x plus 0. But the reason it's so powerful is because 0 could be basically anything you wanted. For example, you could rewrite 0 as 4 minus 4. Now generally, if you have an expression that has a pronumeral in it, it's a good idea to imagine starting with the pronumeral and then applying operations to that pronumeral. So for example, for these two expressions, let me go ahead and actually draw their trees. We represent this leftmost expression with this picture right at the top, and this rightmost expression is represented with this picture at the bottom. Now, despite the fact that both of these perform different steps, as you can see here, they're equivalent because it turns out that no matter what value of x you choose, you're always going to get the same answer on the other side. Now, it's impossible for me to test every possible value of x, of course, but let me just show you one example. Let's pretend that we pick the number 4. Now, in both cases, we're going to multiply the 4 by this number, 3. And then on the other side, we get a 12 here, and we also have a 12 over here. Now that means that 3 times x, when x is equal to 4, is the same thing as the number 12. But this term over here isn't complete. We notice that once we have the 12, we have to add 4 to it, so we're going to have 16 over here. And then to finish things off, we just have to subtract 4 again. So of course, that's just going to bring us right back to the number 12. So we have a 12 over here. Now, as you can see, when I set x equal to the number 4, both this expression and this expression evaluate to the number 12. Now, for the expressions to be equivalent, they need to evaluate to the same number, no matter what number you choose for the pronumeral x. Now, as I said, you can show equivalence with any of these three signs, but another really popular way to show equivalence is to just basically put the expressions on new lines. I'll go ahead and do that with this one over here. Now, instead of adding 0, we can also make an equivalent expression by just multiplying by the number 1. So let me write that down too. Now, you can write 1 in a whole bunch of different ways, but let me just write it down as 3 divided by 3. Now, we'd say that this expression here and this expression down here are equivalent, because no matter what you let x be, both this expression at the top and this at the bottom will evaluate to give you the exact same number. I can show you this with one example, just like I did over here, by drawing out each expression one by one. So in this top expression, we start with x and just add 2 to get our answer. In the bottom expression, we first add 2, then multiply by this 3, and then divide by this 3 at the bottom. Now again, I can't possibly check every possible value of x, but let me just choose one just to show you. Let's pretend that x was equal to the number 1. Well, in both cases, if we add 2, we just end up with the number 3. So at the top, the answer is just 3, but at the bottom we have to keep going. So if we multiply by 3, we get 9, and then if we divide by 3 again, we'll just be back at 3. Now, just like adding 0, the multiply by 1 trick is incredibly important, and you're going to see people do it very, very often. Sometimes you can take a really hard problem, and then multiplying by 1 somehow turns it into a really easy problem. Despite this, however, I would say that these two equivalences here are actually pretty easy equivalences. The study of algebra, which you'd likely be embarking on right now, is the study of finding more interesting equivalences. So the whole idea of studying algebra is to learn the general techniques that can help you find a whole bunch of other equivalences that are perhaps a bit more interesting or a bit more complicated than these two that I've shown you here. Just to give you a taste of things to come, let me show you two equivalent expressions that you're going to be able to prove are equivalent using the rules of algebra. Now, I'm not going to prove this to you in this video, but I'm going to tell you that 9x squared plus 6x plus 1 is completely equivalent to 3x plus 1 all squared. Now, if you started with some random value of x, I'm not saying that you're going to do the same things to it on the left that you're going to do on the right. But what I am saying is that when you evaluate the expression on the left and the expression on the right, you are always going to get the exact same answer. To prove this to you, let me draw out the computations for both this expression and this expression. Let me start with the left computation first. Now on the left, we start with the letter x, and the first thing we do to it is that we square it over here. This symbol over here can be read as the power of, so I'm raising it to the power of 2. After this, if we square x, then the next thing we do is we multiply it by the number 9. Now that we've finished writing out this term, we can look at this term over here. If we again start with the letter x, we notice that we're multiplying x by the number 6. So if we take the number that we get by squaring x and then multiplying it by 9, and the number that we get by multiplying x by 6, the next thing we're going to do is we're going to add them together. So let's do that as well. And then finally, after all of this, we then take this whole expression and then add the number 1 to it, right at the end. So now let's look at the expression on the right as well. Notice that for this expression, we again start with x, and the first thing we do is that we multiply it by 3. So that means if you started with x and multiplied by 3, you have 3x over here. The next thing we're going to do is we're going to add on the number 1. Now after you've done this, you have 3x plus 1. When you have 3x plus 1, you then just have to square it to get the final answer. So my claim here is that this computation over here and this computation down here always produce the exact same answer. And I don't know about you, but that's not obvious to me. Now I can't prove this to you in general just yet, but I will do it very soon. But for now, let's just test that it's true for at least one value. Let's try when x is equal to the number 2. Okay, so for starters, you can take the number 2 and then square it, which will give you the number 4. After this, we can multiply 4 by the number 9 to get the number 36. Now, before you can actually go ahead and add anything, you have to know what you're adding. So we need to go back to this 2 and multiply it by 6 to realize that this number over here is the number 12. Next, we can take the number 12 and add it to the number 36. This is just going to give us the number 48. So this number here is 48. And then if we just add the number 1 to it, we get the number 49. Or to say this another way, if we replaced every x in this expression on the left for the number 2, then it would evaluate to the number 49. You can try this in a calculator if you like. If you just wrote this expression in your calculator, but instead of writing x you wrote the number 2, you will get 49. This is because the calculator, on the inside, is just performing these exact same steps in more or less the same order that we perform them. But we're saying that this is equivalent to this. So if I replace x for 2 on this second expression, then if we follow this list, we should again get the number 49. Okay, so for starters, if we multiply 2 by 3, we'll just get the number 6. If we then add 1, we just get the number 7. If we then square 7, isn't 7 times 7 the same thing as 49? Now, it's pretty natural to be a little bit skeptical about this. The idea is that this expression on the left and this expression on the right will give you the exact same answer, no matter what you choose x to be equal to. That's why we're calling them equivalent. They will always give you the same value, no matter what the value of x is. Now, there are lots of different ways that we could have rewritten this expression on the left, and lots of different ways that we could have rewritten the expression on the right as well. Now, in a sense, when I think of algebra, algebra is a little bit like navigating a forest, like this one I've drawn here. You start off with some random expression, and that's like starting at some random tree. Now, the idea is that every single tree in this forest represents another expression that you could write down. And somewhere in this forest, there's actually another tree that represents the expression that you actually want. And then in a sense, algebra is the study of figuring out how to actually navigate this forest to get from some starting expression to an expression that you actually want to find. Now, as you learn to navigate this forest, you're going to find that there's more than one way to get to your answer. But I've actually gone ahead and grayed out some of the trees. Now, these trees represent expressions that do not give you the same answer when you put in a particular value. Or in other words, these gray trees over here are not equivalent to these trees that you're actually allowed to navigate between. Now, in this lesson, I'm not actually teaching you how to go from one expression to another. I'm just trying to explain to you that there are such things as equivalent expressions. Throughout the rest of your studies of algebra, you're going to learn exactly how to navigate this forest and all the best ways to do it. So that just about sums up all the things I wanted to show you. So let's just summarize everything. So in this lesson, I gave you a definition for what an expression is. An expression is basically a way to represent a series of steps. After this, I told you what a pronumeral was, which is just a value that you use as a placeholder for a number. After this, we talked about the idea of a term. Terms are basically parts of an expression that are separated by plus signs or minus signs. You can also have subterms inside of brackets as well. After this, we explained that it's possible to come up with expressions that are actually equivalent to each other. Equivalent expressions always produce the exact same value when they're evaluated, no matter what the value of any pronumeral in the expression takes. We found two very simple ways to produce equivalent expressions, which is to add 0 or to multiply by 1. And we also said that we can denote equivalence with any of these three symbols. But then finally we said that algebra is a general technique that we can learn to find a whole bunch of different equivalences. And I just showed you one of these in an example. As you continue your studies of algebra, you're going to find a whole heap of different ways to generate different equivalences. In general, you want to find equivalent expressions because sometimes you can reduce the amount of work you have to do, for example, or you can turn a really complicated problem into a really simple problem by finding an equivalent form that's much easier to solve. So that just about completes everything I wanted to say about expressions and equivalences. So as you continue your studies of algebra, you're going to find a whole bunch of different techniques to find a whole bunch of useful equivalences. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.